This is Jim Hendershot again. Our next lecture is number 22, and this lecture covers the topic of how to calculate the performance of an induction machine driven by an inverter. This is, we'll see how we can do getting through this. Here's a very nice phasor diagram for the single phase of a two-pole induction motor. This is this is actually, if you go on Professor Ryaz's website, there's an animated version of this you can use. And what this shows the conductors of a two-pole stator and a two-pole rotor, and a phasor diagram of this rotating. In the rotor reference frame, the rotor speed is 0, but the flux density wave represented by the space vector B sub m, or equivalently by the magnetizing current here, now moves at a slip speed with respect to the rotor, introducing in the rotor are slip frequency currents, which are sinusoidally distributed. The result is seen as a sinusoidally distributed rotor winding whose axis is represented by the space vector I sub r. That's this one here. Both winding and space vector I sub r rotate at the slip speed of the stator. Similarly, the stator space vector IR, which compensates for the rotor effects and the resultant stator currents, the stator currents all move at slip speed. So it's very interesting when you see this rotate in animation that these are the currents flowing into the stator and into the stator and out of the stator, and to form the two poles. And here's the currents flowing into the rotor and out of the rotor. And as in the stator, these same ones are fixed, but in the rotor they move with respect to the speed of the rotor. So during the transition period here, this whole set is moving around the rotor such that the direction of the current is changing in the conductors that separate the two directions of current rotation. This is the torque speed curve that we've seen before, and this shows the motoring and the generating section. And what the induction motor does is pick any combination of voltage and frequency to generate a torque at any point in the whole family of these curves that represent the envelope of performance from the motor and the drive. But we can calculate the performance by three methods. We can use the equivalent circuit method, the vector diagram method from the equivalent circuit, or a motor circle diagram. And these are all explained in a fine book by Paul Cochran. There's the ISBN number. These are compared. I'm not going to repeat them here. And they're not all useful for the motor diameter. I think the vector diagram and the motor circle diagram analysis are more useful for the inverter guy than they are the motor guy. But the equivalent circuits method suffices for the motor engineer. It's the fastest way to calculate the performance, but you either have to calculate all the equivalent circuit parameters, or you have to measure them all from an actual motor. And the measurement of the reactances aren't so. The measurements of the reactance are easy, but the calculation of the reactance are difficult. In lecture number 18, the rotor and stator resistance calculations were outlined. The applied voltage is always given in the specification, so we don't have to calculate that. The frequency choices are based upon the pole number in the machine we're talking about, the slip and the speed. This leaves us with the magnetizing current calculations for a given load point, along with the three inductance parameters to determine. Now the phase current is, as we've seen before, is here's our phase current vector, and we have to break that current vector up into two components. One vector produces a torque that rotates in the rotor bars, and the other is a magnetizing current that rotates in the stator phase windings, along with this one too. Because it has to induce it there into the rotor. The torque producing current is a vector determinant of the phase current and the magnetizing current. We always want the magnetizing current to be the lowest, as we said before, to maximize the power factor. But we don't want to over-magnetize the machine. We want to only provide enough magnetizing current at any given load to achieve the desired load point. We don't the constant volts to hertz drive keeps the ratio of voltage constant, whereas in a flux vector drive you don't have to do that. All you have to do is supply sufficient magnetizing current to achieve the desired load point. This way you operate at a high power factor over a wider speed range and higher efficiency over a wide speed and load range. The magnetizing current calculation can be calculated with this formula here, and of course we talked about earlier that the Carter coefficient has to be used to account for the effective difference in the air gap length due to the slot openings. And so there's some teeth saturation coefficients involved here as well, but you wind up with a formula for the magnetizing current. Then the leakage inductance, the stator leakage inductance. Here's the calculation and the legend for calculating the leakage inductance, and the slot leakage coefficients. Here's the procedure for that. And deeper slots, larger slots have higher leakage reactance. Wider slots with large slot openings have smaller leakage reactances. This is true of the rotor or the stator. By the way, these are Baudet's methods, Professor Baudet from Romania. The differential leakage coefficients, zigzag rotor leakage, is calculated by using these formulas here. The end leakage coefficient calculations, and the rotor leakage inductance. And this is very approximate, but it consists of several components using some equations and some empirical formulas, and this is a very difficult to accurately predict. It requires finite element solutions to actually estimate these leakage inductances. The rotor differential inductance, here's the formula and the expression for that. Two types, zigzag and belt. And the rotor end leakage inductance. These are the rotor end leakage inductance. Depending on the number of poles, of course, it goes up with the number of poles, the number of rotor slots, and the machine axial length. Here's a very nice picture of the equivalent circuit when it ties it into the physical components of the machine. And this is a basic torque equation for the shaft torque at any speed, not counting windage or friction. But this is a very important formula that gives you the torque calculation in Newton meters. Using Thevenin's theorem for torque calculations from the equivalent circuit, he came up with a theorem that greatly simplifies the torque and power calculations from the equivalent circuit by leaving out the core loss term. And you can check this IBN publication, page 332, for a detailed analysis. But his equivalent circuit becomes this expression here, where there's a simple voltage divider and the impedance between terminals A and B viewed towards the source and set to 0 like a short circuit. So Thevenin's formula for torque is given by this expression here. So this torque equation can be used then to generate any of these torque versus speed curves at any fixed voltage and frequency. And so what would you do with that? You would use that to define the 5 or 6 load points on the torque speed curve for the machine and the inverter that you're designing to define this envelope. So each one of these is a fixed frequency and voltage, and the magnetizing current is minimized for each one of these points, and that defines the output capacity of this machine. That's the end of this lecture. Thank you.